Hello, and thank you for listening to my talk about CPT violation in neutrino oscillations. As you know, neutrinos are produced in charged current interactions as weak eigenstates, and these weak eigenstates can be written as superposition of mass eigenstates weighted by the entries of the lepton mixing matrix U here. The time evolution of the mass eigenstates is given by this formula here, which is obtained by solving the free Hamiltonian for neutrinos. Now the time evolution of the flavor state is immediately obtained by substituting nu k of t here into nu k. So this means that after some time t, the neutrino which had initially a composition of u alpha k will have a different composition due to these parameters here. So this means that the neutrino, which has been initially in nu alpha, can be detected in a different state nu beta, and the transition amplitude is given by this formula here. From this formula, we obtain immediately the neutrino oscillation probability by taking the absolute value squared given here. So in general, the mixed matrix U here can be parameterized in this form as a sequence of 3 rotations. So we have 3 mixing angles, theta 1, 2, 1, 3, and 2, 3, and the Dirac phase delta, which is going with the 1, 3 rotation here. We have 3 masses, M1, 2, and 3, which can be arranged in 2 different orderings. Either the neutrino with the largest electron neutrino content is the lightest neutrino, or the neutrino with the smallest electron neutrino content is the lightest neutrino. In the first case, we talk about normal ordering. In the second case, about inverted ordering, and this corresponds to the sign of the parameter delta M31 squared. Good. So in the standard picture, all of the 6 neutrino oscillation parameters, so the 4 parameters which characterize the mixing matrix U and the 2 mass splittings, are more or less well measured, as shown in this picture here, where the blue lines are for normal and the magenta lines for inverted ordering. However, these profiles are obtained under the assumption of standard neutrino oscillations, so no new physics scenarios are considered in the calculation of these profiles. So now, in the following, I will talk about CPT violation, and we will test if the CPT theorem holds in neutrino oscillations. So to do that, we basically assume that neutrinos oscillate with one set of parameters, and the antineutrinos oscillate exactly in the same way, but with a different set of oscillation parameters. Now, if CPT symmetry holds, both of these sets have to be equal. So in the current experiments, we find that the best fit values often are not the same for neutrino oscillation parameters and antineutrino oscillation parameters, but there is significant overlap even at 1 sigma level, as is shown here for T2K in the left 2 panels and nova in the right 2 panels. So you see that for in blue, we have the neutrino parameters, and in red, the antineutrino parameters. In the right side, we show the profiles for the parameters for the combination of T2K and nova data, and the black lines correspond to the combination of T2K, nova, and reactor antineutrino data. So you see that there is more or less good agreement between the neutrino and antineutrino parameters. So one interesting feature that we can see actually from the lower panels here is that the CP phase is very weakly determined. So basically, using the T2K or nova neutrino antineutrino data, we find that using only neutrino antineutrino data, there is no way to measure the CP phase. So you see that all of the values here are always below a chi-square level of 2. So even when combining all of the baseline data for neutrinos and for antineutrinos, this situation does not improve considerably. So you see still for the neutrinos, the chi-square curve is always below 4. And even adding the reactor anti-neutrino data on top of the long baseline data does not improve this situation, as you see here. So even all of the values are allowed with a chi-square of less than 1. So this means that in this CPT violating picture, a measurement of the CP phase is not possible. And this is not surprising, because the CP phase adjusts the spectrum for neutrinos differently than for the antineutrinos. But if we allow for different 1-3 angles, this job can be done by the 1-3 angle directly instead of the CP phase delta. Okay, so we can use the same data, however, to put bounds on the differences of neutrino and antineutrino parameters. So here we show the 3 sigma bounds from the current long baseline and reactor data, which are also shown here. So you can also see the important impact that the reactors have in setting bounds on the theta 1-3 angles and on the mass splittings. Of course, the bounds that we see here for delta m21 squared and sine squared theta 1-2 come from the analysis of Kamland and solar data, not from long baseline and reactor data. So now let us see how this can be improved with the upcoming DUNE experiment. So to generate the fake data, we have used these parameters here. And as you can see, we assume 3 different scenarios for the atmospheric angle. First, we assume it to be in the first octant. We assume maximal mixing, and also we assume a second octant value. And we find that there is very poor sensitivity to improve on the difference of CP phases or on theta 1-3 angles. Let me mention here that in the analysis of this data or this fake data, we assume a prior on the reactor angle in the case of antineutrinos. So the situation changes when we go to the atmospheric sector, where we find that DUNE can improve the bounds. So in particular, we have that DUNE can set at least this bound here, 3 sigma, for the difference of atmospheric mass splittings. In the case of the atmospheric angle, we have an increasing chi-square profile as expected for maximal mixing. However, something more interesting happens if the angle is not maximal. So as you can see in this figure, our profile first starts growing, but then falls again. And this, of course, appears due to the degenerate solution in the measurement of sine squared theta 2-3. And this means that if CPT is violated in nature, and the difference is around 0.17, DUNE would be blind to see this effect. So this brings me to another interesting topic in the context of CPT violation, and this is the topic of imposter solutions. So the question is, how big is the error that we commit if CPT is violated, but we analyze the data in a CPT conserving way? And to do this, we have generated a fake data set for DUNE, assuming maximal atmospheric mixing for neutrino parameters and a first octant value for the antineutrino parameter. So the profiles correspond to the red and the blue lines here. However, in the CPT conserving combined analysis, we obtain a best fit value, which is in between of these two values. And in particular, we disfavor the true values of oscillation parameters at around 3 sigma confidence level and at even more than 5 sigma confidence level in the case of the antineutrino parameter. So this can also happen for other parameters, as shown here for two scenarios of data. So in the left panel, we have created the data with delta equal to 0 for neutrinos and 0.5 pi for antineutrinos, and on the right side, vice versa. You see that in particular, the 0 value is excluded at close to 5 sigma and more than 5 sigma here on the right side. So how is the possibility to observe CPT violation in Dune? So we have seen before the analysis of T2K and NOVA giving different best fit values for neutrino and antineutrino parameters. But here there was significant overlap even at 1 and 2 sigma confidence level. So we have used these parameters as an input and created the fake paper for Dune. And you see that only at the 4 sigma level for 2 degrees of freedom, there would be an overlap between the antineutrino and the neutrino region. So the 3 sigma 2 degrees of freedom regions are completely disjoint. If we put this into a 1D profile, we see that the CPT conserving value of 0 would be excluded at close to 5 sigma confidence level. So in case of such an observation, one has to be a bit careful, because there could be mimicking effects between CPT violating neutrino oscillation parameters and NSI. So what we did here is that we created again the same fake data set as here, but we analyzed it in a CPT conserving way with NSI. And you see that, the result is basically the orange curves here, and that the data can be fit in an excellent way with a relatively large value for epsilon tau tau. The black line here is the current bound. So you see that the best fit value that we obtain would be basically already excluded, but there is some transition zone where the bound is not so strong, and we would still obtain a very good fit of the data. So in this case, one could not distinguish CPT violation from non-standard neutrino interactions. Okay, so this brings me to my conclusions. So we have seen that the determination of neutrino oscillation parameters worsens a lot in the presence of CPT violation, as might be expected. Dune can improve some of the bounds on the differences of neutrino and antineutrino parameters, in particular in the atmospheric neutrino sector. We have seen the danger of analyzing data in a CPT conserving way, because imposter solutions can arise in these scenarios. And we have seen that in some cases, Dune could distinguish CPT violation from non-standard interactions. Thank you.